So love them or hate them, I have some of these fill in the blanks. I have, I think, a total of 3 of these. If I tell you that the law of conservation of energy is the same concept as the conservation of mass and matter, which you've already learned. So pause the video and fill this out, and then I'll have it filled out when you... Okay, so you should have gotten that for the law of conservation of energy, energy is neither created nor destroyed. After a phase change, we're going to describe that in a minute, or a chemical reaction, there must be the same amount of energy as there was initially, but it could be in another form. We've already talked about how energy can change forms. Also remember that conservation of mass still applies to chemical reactions, so that the total mass or amount of matter in a system does not change during normal chemical reactions. The atoms are rearranged. I'm pretty sure you can also figure out most of these. So pause the video. So we'll just read through this. Thermodynamics is the study of the movement of thermal energy from one source to another. We call the transfer of thermal energy heat. And you've already seen that cue from the other page. There are 2 types of heat exchanges in general chemistry. We have phase changes and reactions. Life experience shows that adding heat to an ice cube will cause it to melt. This is a phase change. Notice that the ice cube, when it melts, it started off as water, just in the ice form, and then it became water in the liquid form, right? It didn't stop being water. So that's why we call it a phase change. It's changing from the ice phase or the solid phase to the liquid phase. Experience also shows that burning wood, a chemical reaction, generates heat. Potential chemical energy is relevant because energy is released when bonds are formed, and then the second part of it is, or absorbed when bonds are broken during reactions. Potential chemical energy is converted into kinetic thermal energy. So thermal energy is a type of kinetic energy. And the reason that it's released when bonds are formed is if you imagine 2 atoms, and remember in chapter 5 we talked about how there's that perfect distance where they can have that overlap, and it makes both atoms happier because it gives them both a total of 8 electrons. So it's a low energy state. So alone they had more energy, but when they came together, this was the lower energy state. So it's kind of like 2 magnets. They get really close and they're like, oh, I want to match up really fast. That's what happens. And so because it moves into this lower state, it releases some energy. Likewise, when you're absorbing energy when a bond is broken, it's because we're having to go in and do something to make that bond cut in half and pull the 2 atoms apart. We're forcing that change. And so that's why you have to put in energy. A lot of times that energy that you're adding in is heat. It's not like you're going in and individually mechanically pulling them apart. A lot of times it is heat, but I'm just saying that they're absorbed when bonds are broken during reactions.